Hello. Last time we spoke, I did a video on using stats and normal distribution to basically find probabilities using standard normal. So just a quick recap, because this lesson I want to do 2 points to basically create part 2 of this lesson, where the first thing I want to do is, if we have a probability that isn't standard normal and it's just normal, how we convert that to standard normal and then use the same table. And then secondly, I want to do a bit on finding percentiles and also interquartile range, etc., using standard normal. So if I was to just do a quick recap. So last week we did standard normal, distribution. Yep. Where you might recall, if I have a variable, and normally they use Z if it's standard normal, the notation to write is n with 0 and 1. And if it's 0 for mean, 1 for variance, that is what they call standard normal. Yeah? And just to be extra clear about this, there are 3 sort of calculations I can use, right? And when I say calculations, I'm saying this sort of standard normal table here is very common, where they have the first, the unit or the integer before the decimal, and then the first decimal place after. Sometimes you'll see this table where they have the first decimal place on the left, and then the second decimal place running across horizontally. So just so we can use that. So when we see this distribution of standard normal, so we can have probabilities where Z is less than, let's say, for example, some positive number of positive 2. Right? If that happens, what we're basically saying there is the graph for this looks like, where obviously if it's standard normal, the mean is 0. This probability basically says I want everything below the value of 2. So this area here, and then if it's less than, I can quite simply access the table. So for this, quite simply use standard normal table, yeah? Which is basically that table over there. Yeah. So, and just to save us a little bit of time today, whenever you see this notation where it's less than 2, in textbooks and stuff, to simplify the notation, they basically use a Greek capital letter of phi of 2. So whenever you see this notation, it means exactly the same thing, right? Where the standard normal is less than 2 or less than or equal to 2, they just write phi 2, right? Now, so that's the first calculation that we do, right? Where we basically access the table. Also, what happens is sometimes they might want to say, so there's 2 sort of variations of this, where the first variation in the table, they can go, if I take a negative number for standard normal. Now, diagrammatically, on the standard normal, once again, if this was 0, the negative 2 would be here. I'm going to utilize the symmetry properties of a standard normal graph to basically say, well, this is the same as this area here is the same as this area here, right? They're equivalent, which means that if I found the area leading up to that, right, because blue plus green in this case adds up to 1. If I take 1 minus the area of the blue, I should be able to get green. And I know that because of symmetry, if this was negative 2, then that positive number would be 2. So I'm going to go green, which is what I want here, with the negative 2, is equal to 1 minus the blue. So what I want you to see is that if you wanted Z less than or equal to negative value, you just go that equals to 1 minus the probability of Z less than or equal to the positive equivalent. So just equating that using the new sort of phi notation. So they want a phi of a negative number that equals to 1 minus phi of positive. Second property. So this is what you do when you use negative numbers. And the reason why this is important, it's more because of the table. Because the table you can see has no negative Z values. It starts at 0, right? Because of symmetry. So we basically used symmetrical properties to derive a relationship between the negative number and the positive. And obviously, the third sort of calculation that is very common is when z is taken between two numbers. Right? Let's say, for example, 1 and 2. Right? And if that's the case, you basically take, and once again, diagrammatically, right? I guess it's always good to relate it to the diagram because then you can understand where these sort of relationships and formula came from. So this property, this value here wants the area between 1 and 2, which is basically this area here. Then you can sort of see that I'm going to take the area leading up to the 2 and then minusing the area leading up to the 1. Right? Area up to 2 minus that blue area. So what you get there is basically P of Z less than 2. Right? So that's the area that takes you from that blue all the way up to the green. And then less the probability of Z less than or equal to 1, which is basically the blue. And then you will get the green. Once again, using, well, let's just put that as our third box. You can put that in phi notation. Yep. So those three calculations are very common in this topic. Now, the next thing I did, so that was what we did last week, although I didn't use the notation, I did calculations on that. The other point to make is, if you're ever given a random variable that is not standard normal, but is just normal with some sort of mean and some sort of variance, right? So a normal distributed variable. So we don't actually have a table that has mean and variance. So what we do is we do a conversion, right? Where we basically convert this into Z, right? Where Z equals to whatever X value I have, subtract the mu, divided by sigma, right? So this conversion takes us from normal to standard normal. Let's do a few examples that illustrate this point. I'll do over here where I've, not by coincidence, have a table here. So if I do, let's say 3 easy examples where I say for a standard, or sorry, for a random variable that is normally distributed with mu and sigma squared variance, comma find, and I'll give you 3 examples just to run this through quite quickly. X is less than or equal to 6, where in this case mu, let's say, equals to 4, and sigma equals to 2. Maybe I'll write down all 3 first. So P, where let's do one that's in between 5 and 9, say, where let's change up the expected value, say 10, or sorry, 3, and sigma is 10. Maybe one more to illustrate something a little bit different, where 3 less than or equal to X less than or equal to 11 looks very structurally the same as B, but when you do it, you'll see that there is a slight difference. So 4. 3 examples, 3 quick ones. So for the first one, you can sort of see in the question that it is not standard. So I got to turn that using the formula I did before, right? So Z equals to mu minus, sorry, not mu, it's, X minus mu on sigma. Right? I'm going to use this formula to convert each one of these normal variables into standard normal. So part A, where I want X is less than or equal to 6, to convert that into Z, right, or standard normal, I'm going to take whatever X value that I wanted, minus mu, and divide by sigma, right? Pretty easy. So that one there is equivalent to Z less than or equal to 1. And once again, if I was to go to my table here, 1 is like 1.0. So I'm expecting this guy here to be my answer, because that's 1.0 here. So my answer for this one, you can write it as phi 1 or just probability of Z less than or equal to 1, 0.8413. Pretty straightforward there. Now part B. So in this one, I want the values of X between 5 and 9, where I know X has mu of 3 and sigma of 10. So I'm going to convert this into an expression that has z in the middle, where I take each of the 5 and the 9, subtract from both of these the mu, and divide both of those numbers there by sigma. Quite straightforward, right? So that's that. What 2 on 10, so 0.2 and 0.6. And just like the previous slide where I said if z is between two numbers, you basically take the area up into 0.6, subtract the area up to 0.2. Maybe you can save yourself a bit of time there if you used the phi notation, but let's persevere with that. That's 0.6, so where's 0.6 on this graph? That's this guy here, so 0.7257. Just quickly note that down. 7257 minus now 0.2. 0.2 is this one. Right, make sure you copy that down. What's that? 0.5793. If you do that on the calculator, hopefully you get 0.1464. Yeah. So hopefully that's okay, right? And the last one done in a very similar vein. For part C, if they want probability that x is between 3 and 11, so same type of calculation there where you take the probability of z, right? You start with the 3 and the 11, subtract from both of these the average of 4, and also for this question, the sigma is 4 as well. Right, so you're basically finding the probability, what's that, negative, that's a negative quarter, so negative 2.5, z, that's 1.75, is it? Let's just note to yourself though that for this one, 0.2575, I don't have that second decimal in this particular table. Some tables have it, some tables don't. So this one, I just take the nearest one. So to be clear, maybe round that up. That's like approximately probability of negative 0.3, so probability of 1.8. Now, so once again, if I'm in between two, I would say that's the probability that, maybe I'll use a phi notation just to save me some time. 1.8 minus 5, negative 0.3, and just to be clear there, see this guy here, negative, right? My table doesn't have negative, so I'm going to use the symmetry properties there of 1.8 minus symmetry properties means it's 1 minus its positive, right? Of 0.3, and then now I can access the table. So 1.8 is 0.9641, and 0.3, let me quickly look up, 0.3 is 0.6179. 6179. Yeah. If you punch it in the calculator, see what we get. So we get 0.9641 minus 0.6179. 0.582. Just going to zoom out. So for those that are taking screenshots of this, right? That's how you do it. So 3 very common questions where you start from a normally distributed variable, convert that to standard normal so you can use the table itself. So the next thing I wanted to show you was this concept where we basically try to find things like percentiles and stuff where you almost go backwards, right? For percentiles, and I'll show you what I mean by that. So let me give you an example, just to illustrate this, and the interquartile range as well. Yeah, which touches on that rule where you use the interquartile range to find outliers. So as an example, if I have so maybe I'll say if for, a better question would basically have words like for a random variable x or continuous random variable x, z or stuff like that. But let's just skip all that and go, that one's normal. All right, so standard normal immediately. Yep. So part A, using interpolation. Okay? Whenever it says interpolation, right, if it doesn't say anything else, you can assume linear because you can actually have a number of ways of interpolating, but let's assume it linear. So straight line interpolation, find the value of z that represents the 60th percentile and to the upper and lower quartiles. And then part B, using the interquartile range rule, what percentage of results can be considered as outliers? So basically, if a random variable is standard normally distributed, what percentage of scores or results can be considered as an outlier? Now, that's an interesting question. Now, the way we do this is, so we're going to go backwards a bit, where in this case, right, if they give you the 60th percentile or the upper and lower quartiles, right, because that's upper and lower quartiles are basically 2 percentiles where, just to be clear there, upper quartile is like the 75th percentile and the lower quartile is like the 25th percentile, right? So theoretically, I can infer that just by understanding what upper and lower quartiles are. So in this case, they give you the percentile, right? They give you the percent that is equal to, right? But they're asking you to find Z. Yeah? So this is how, this is basically what the question is trying to say. It's basically saying the probability of Z less than a particular value of Z, right? Capital Z is a variable, Z is a value on the curve that I want. So just because, what does it mean by the value on the curve? It means that right now, that's 0. So all these values on the x-axis, they're value of Z's. The question is saying, what value of Z is it? Where am I horizontally such that it represents the 60th percentile, so that the probabilities, right? So this is the value of Z, and I don't know what that is, right? But I do know that the sum of this area here equals to 0.6 or 60%. Yeah. So I need to find the value of Z that has an area of 0.6. And so what I do is I sort of go backwards from the table, right? I say to myself, I go to the table. So let's go back to this table over here. I want the numbers in here, because the numbers in these in this matrix here represents the percentages, right? So I want the numbers that are closest to 0.6. Now, there's no number you can see because they're like 4 decimal place. There's no number here that's exactly 0.6. So I'm going to use what they call interpolation to find. So I'm going to find the closest ones. So that guy there and that guy there. So I know that the value of Z that I want is going to be between 0.2 and 0.3 because 0.6 is in between there, right? So this is what I'm going to do. I'm going to teach you how to do this by interpolation, right? So from table, yeah. Now, by the way, using the new notation, right? This guy here, yeah. From the table, I can see that if I looked at 0.2, it's 0.5793. So 0.2 is equal to 0.5793. Also from the table, 0.3, right, if you looked at it perfectly, 0.6179. Now, I want the value exactly to be 0.6 or you know, close to 0.6, which means, what am I trying to find? I know that somewhere in between, actually, maybe I'll write it like this so you can sort of see what I want. So somewhere in the middle here, right, there is a Z value that gives me exactly 0.6. That's what I want. So I'm going to interpolate this, right? Now, what does interpolation mean? And I'll use a different colored pen to give you an idea. So remember, Basically, these two green lines here both represent a point on the graph. And if I connect the dots, there's a straight line that's created. I want to know along that straight line which z value gives me 0.6. So you can imagine if I use coordinate geometry to help me here, right? Y minus y1 and x minus x1, right? Yeah, where in terms of the black, this guy here is like x, this guy here is like y. Yeah, that's my x and y. I'm going to sub this in later to try to find what z is. But the green gives me information for this, right? Because if you can imagine, this is like x1, this guy here is like y1. So that's like the first point. This guy's like x2, and this guy's like y2. Now, I'm going to try to find the gradient first, right? So the gradient in this case is going to be y2 minus y1 over x2 minus x1. Yeah, if you punch it into the calculator, I think you get 0.393. Yeah, you can check that yourself. I'm prone to doing arithmetic errors. But once you get the gradient, I'm going to sub in this point into the x1, y1, and I'm going to sub in this black line into here to try to find z, right? This is the key. I want to try to find z. That is the whole purpose of me doing what I'm doing now. So let's sub everything in, right? So y is 0.6. y1 is 0.5793. I just found the gradient, right? This guy here, so 0.393. Now, this x value is basically what I want to find. Yeah? So I'm going to let that be z minus x1. If you did your awesome maths and found z to be 0.25, that's what I got. What that means, that value there is my 60th percentile. So if coming back to the graph upstairs here, if you found the z, let the z value be 0.25, that would represent, because 0 is in the middle, right? 0 is obviously 50%. If you did 0.25, that represents 60% of all scores or all results. Yeah? That's what the 60th percentile means. Now, if that sort of was a bit hazy and a bit quick, I'm now going to do the same thing for the upper and the lower quartile, which is exactly the same calculation. The only thing that changes, instead of 60%, instead of 0.6, it's 0.75 and 0.25, right? So you get 2 more cracks at understanding this concept, right? 2 more goes at this. Let's have a look. Just going to do this so I can write a bit neater. So for the upper quartile, right, which I think people write that as Q1, but let's just say upper quartile. Yep. So I know that this one here, the probability of z less than or equal to z equals to 0.75, right? So on my table, right up here, I want to find the 2 values that are the closest to 0.75. Let's see. 0.7, this guy and this guy, right? So it's going to be somewhere between the 0.6 and 0.7, right? That's the z value, and that's what the probability equals to. So I'm going to jot down these 2 and use those as my 2 points, and then I'm going to interpolate. Now, just to be clear, if you think about the symmetry case, right? 0.75, now I know if I can find the z value here, that gives me 75%. So this is 75%. Does it make sense? Because of symmetry, if this guy here is 25%, does it make sense then, right, to find the lower quartile, which is 25%, does it make sense then, whatever z value this is, this will be negative of that z value, right? So in other words, if I find my upper quartile, whatever that z value is, negative of that will be my lower quartile because it's fully symmetrical, right? It's fully symmetrical. So all I need to do is find the upper quartile and then infer the negative case to be my lower quartile. So now, from my graph, so from my table, right? I found that phi of, what was it, 0.6 and 7, 0.6 is this guy. 0.6 is 0.7257 and 0.7 is equal to 0.7580. Right, so it's somewhere in between, right? And once again, to be extra clear, this guy here is x1, this guy here is y1, this guy here is x2, this guy here is y2, right? So using and also this guy is my x value, this guy is my y value, right? Sub all that in, so y, also I need to find the gradient first, right? Let's find the gradient first. So the gradient is equal to y2 minus y1 divided by x2 minus x1. Brilliant. If you did that on the calculator, the gradient is 0.323. That's a slightly different gradient to before because between different 2 points, you'll get a different slant, right? So don't use the same gradient as before. Therefore, y minus y1 equals the gradient x, which is now z, right? Minus z1, oh, sorry, x1 rather. If you made z the subject there, hopefully you get 0.675, right? In other words, this guy here is therefore upper quartile when z equals to 0.675. And like I said before, if that's the upper quartile, then the lower quartile is symmetrically negative 0.675. Yeah, which is interesting. So that gives me an interquartile range of upper minus lower of this guy minus this guy is exactly 1.35, right? Yeah, I'll need these three numbers when I do the next part. Is that okay? So, oh, sorry, I did, this is part 1. This is actually part 2, isn't it? B. So part B. Now part B says using the interquartile range. So in other words, if I graph this symmetrically, right, and obviously that's 0, there's some scores right out here in the tails that are considered outliers, right? Yeah, these guys are outliers. I'm going to use the rule that the IQR rule that suggests that of identifying outliers. Now, for those that have forgotten, the outlier rule or the IQR rule for outliers is, and I'll write it in green here, to be an outlier, right? You either, there's the positive outliers and the negative outliers, right? So for the positive ones, you basically take the upper quarter and you add 1.5 of the interquartile range, right? And for the lower one, you take the lower quarter and you minus 1.5 of the IQR. Yep, actually, can I ask a favor? I'm just going to shift this over here or below here so I can do a calculation there. So what this means is for the Z values, right, of up quartile, I know is 0.675. If I add 1.5 multiplied by the IQR, you punch it in the calculator, you get 2.7. So what that means is, if I take a Z value of 2.7, anything above that, right, anything above this is an outlier at 2.7. Yeah, and you know, you can sub it in and do the maths, but symmetrically, if I take negative 6.75, sorry, 0.675 minus 1.5 of the IQR, you should get negative 2.7 as well. So negative 2.7 will give you the lower outliers. Now, using these two and my graph and my table, right, I can find or try to find the outliers. So what I'm going to do, see if I can space. There's not a lot of space here, right? I'm just going to copy this. This is what I do in my classes. I'll copy this and just remove everything. Give myself a brand new place to do some work. So let's calculate the IQR rule, right? So the percentage. So I want to know what percentage lies outside of in these ranges of green, which means that they're outliers, right? So basically, what I'm after to be an outlier, the percentage of outliers is anybody with Z values greater than 2.7, right? That's these guys, plus anybody with Z values less than negative 2.7. They're these guys. Yeah? And then using my table, I can find this now. Recall two things. These two, see how it's greater than and less than negative? They sort of fall into, can I go back to the very first slide, right? So negatives go into here, and greater than uses a symmetry formula. So I know that this guy is the same as 1 minus the probability that Z is less than 2.7. Yeah, because my table only does less than, right? While this guy, because it's negative, I can't do negative. That's the same as 1 minus, so graphically 1 minus the positive, which is basically equal to, so let's say less than, that's like 1 minus the probability of Z less than positive. Yeah. In other words, if you think about that and that, if you have a quick look, they look exactly the same. So on my calculator, it's the same as punching in 1 minus the probability, oh sorry, 1 minus 5, save myself some time, of 2.7 times 2, yeah, times 2. So on your calculator, now before we do the calculator actually, let's go to our table, 2.7 on there as a final glance, 2.7 is this guy, which means, if I go back there and sub in 0.9965, punch it in your calculator, I believe it's 0.007. In other words, 0.7% of all scores are outliers. Is that okay? So I thought I'd basically summarize for you questions, do some work examples where the question starts off with a normal distributed variable, first, and then you basically convert that to standard normal, and then do some questions where you basically answer try to find the value of Z that gives a certain percentage. In other words, go backwards, you look at the table, and then you use interpolation to try to calculate the value of Z. Yeah? And it allows us to also deal with this outlier concept. That's all I want to do. Till next time. See you guys later.